Welcome to Section 3.1 AI Lifecycle Overview. In this lesson, we'll map out the full lifecycle of an AI system from initial data collection to ongoing monitoring and eventual retirement. Understanding this lifecycle is crucial because it provides the structure, checkpoints, and best practices needed to ensure that AI projects remain effective, reliable, and ethical over time. Think of it as a roadmap guiding every AI project from idea to sustained impact. And now here are the objectives for this lesson. By the end, you should be able to clearly describe the major stages of the AI lifecycle, explain why iteration is not optional but essential, and recognize how real world workflows map onto this structured approach. You'll also gain an appreciation for decision gates, the points where we evaluate progress and decide whether to proceed, revise, or even pause a project. Together, these elements form the backbone of trustworthy AI development. So let's get started. So, what is the AI lifecycle? So, data collection and preparation. Every AI lifecycle begins with data. Teams must gather data that is representative, reliable, and aligned with the problem at hand. Consistency matters. Inconsistent or poorly labeled data can introduce errors before training even begins. At this stage, privacy and compliance requirements must also be respected, whether under GDPR or HIPAA or even internal standards. Think of this as laying the foundation of a house. If the ground is unstable, everything you build on top will eventually crumble. So, experimentation and model building. Once data is prepared, the experimentation stage begins. Here, data scientists select algorithms that match the problem: classification, regression, clustering, or others. Multiple candidates, multiple candidate models are trained, each with different features or hyperparameters. These experiments are not one-off trials. They've systema- they're systematic comparisons designed to reveal trade-offs in accuracy, efficiency, and complexity. Tracking is crucial. Without a structured process, results can't be reproduced and promising insights may be lost. This stage reflects the scientific roots of AI: testing, refining, and iterating to discover what truly works. Validation and evaluation. After training, validation ensures the model's performance is real and not an illusion. Metrics such as precision, recall, and F1 score help capture different aspects of performance, while overfitting checks confirm the model isn't memorizing training data. Fairness and robustness are equally critical. A model that works for one group but fails for another cannot be trusted. Validation acts as a gatekeeper, asking, is this model reliable, equitable, and ready for broader deployment? If not, the cycle loops back to experimentation or even data preparation. So, registration and deployment. When a model clears validation, it is formally registered in a central repository. This registration step is like publishing a product version. It provides traceability, accountability, and an official record. Deployment follows, moving the model into staging and ultimately production. At this point, technical requirements around scalability, response times, and resource usage become front and center. Security is equally important. Protecting model integrity, preventing adversarial tampering, and ensuring compliance with regulations. This phase is where AI transitions from an experimental artifact to a living system embedded in real-world workflows. So, monitoring and feedback. Once deployed, monitoring begins. This isn't optional. It's the only way to know if a model continues to perform under real-world conditions. Performance may decline due to data drift, where, where live inputs no longer resemble training data, or anomalies may reveal hidden weaknesses. User and stakeholder feedback provide additional signals that can't be captured in metrics alone. Monitoring is active stewardship. Without it, even the most advanced models will eventually degrade, eroding trust and effectiveness over time. Retraining and retirement. The final stage involves either retraining or retirement. Retraining refreshes a model with new data, helping it adapt to evolving environments or emerging patterns. Sometimes, however, replacement is the better path. For example, when new techniques dramatically outperform older ones, retirement must be handled responsibly with documentation and governance to prevent old, unsupported models from lingering in production. Closing the life cycle properly isn't failure, it's disciplined practice. Like software updates or product recalls, it ensures that AI systems remain current, safe, and trustworthy throughout their operational lives. The AI lifecycle. The AI lifecycle is not a one time sequence. After deployment, we monitor performance. If accuracy drops or new requirements emerge, retraining begins with a fresh data collection. If a model is retired, its replacement also starts with new data. That's why the cycle closes the loop. Retraining or retirement always lead back to collection and preparation, ensuring the system stays relevant. To recap, the AI lifecycle is circular, not linear. Each stage feeds into the next, with decision gates providing structure and accountability. Monitoring ensures systems stay reliable in changing conditions, while retraining and retirement sustain trust over time. By embracing this cycle, organizations build AI systems that are not only effective at launch, but also resilient and ethical in the long run. This concludes our overview of the AI system lifecycle. We've explored how data, experimentation, validation, deployment, monitoring, and retraining all connect in an ongoing cycle. Remember, AI is never a one time effort, it's a living system that must be managed with care. And that marks the end of this lesson. Thank you for listening.